Where did Earth's water come from? And what if it was never supposed to be here at all? Imagine for a moment in the vast, dead silence of space. A single anomaly, a planet awash in liquid oceans, breaks the rule. Our planet is a statistical miracle. While the Moon, Mars, and Mercury remain dry and lifeless, Earth is blanketed by water so abundant that it shapes weather, sculpts continents, and birthed every living species we know. But here's the shocking truth. When Earth first formed, it wasn't all blue and beautiful. It was hell. A scorching ball of molten rock under constant bombardment from asteroids with no stable atmosphere, no oceans, and absolutely no life. So how did water, the most essential ingredient for life, arrive here in such staggering quantities? Did it seep up from Earth's core, locked away in ancient minerals? Did it rain down from space, carried by icy comets and water-rich asteroids? Or could it have come from something even more ancient, from the very dust that formed the sun itself? What you are about to discover are not just theories, but scientific fault lines that divide some of the brightest minds on the planet. For decades, researchers have tried to trace Earth's water back to its origin. Their search spans billions of years across planetary collisions, vanished protoplanets, and chemical signatures in rocks older than the Moon. One fact is clear: Earth wasn't born wet. Whatever process brought water here, it had to survive unimaginable violence, including the apocalyptic impact that formed the Moon. That one event alone, caused by a Mars-sized body slamming into our young Earth, would have vaporized surface oceans many times over. So the question isn't just, where did water come from? It's, how did any of it survive long enough to shape life? Now scientists are closing in on a few competing theories, each strange in its own way. One theory claims the water was always here, locked inside volcanic minerals, slowly released over eons. Another says it was delivered later by swarms of icy objects from the edges of the solar system. But recently, a third contender has emerged, one that points to a forgotten phase of the solar system's birth, a time when dust gas and ice from a collapsing nebula seeded planets with the ingredients for oceans before they even fully formed. Could Earth's oceans be older than Earth itself? And if so, what does that mean for the chances of water and life on other worlds? As we peel back the layers of planetary history, it becomes clear Earth's water may not be native, but it was chosen, selected through a cascade of impossible cosmic accidents. And that raises a final disturbing question. Is water the norm in the universe? Or are we a rare exception in a desert of dead worlds? To understand how water arrived on Earth, we need to rewind the cosmic clock to about 4.5 billion years ago, the moment our planet began to take shape from a cloud of dust and debris orbiting the young sun. At that stage, Earth was little more than a growing sphere of molten rock. Its surface was unstable, its gravity weak, and its atmosphere non-existent. Life as we know it was impossible. Yet within this violent infancy lies the first major theory. Endogenous origin, the idea that Earth's water came from within. According to this model, water was chemically bound inside silicate minerals deep in the mantle trapped since the planet's formation. Over millions of years, intense volcanic activity would have released steam into the atmosphere. As the planet cooled, the steam condensed into liquid, eventually forming oceans. It's a logical model, and one backed by evidence of hydrogen isotopes in ancient volcanic rocks. But here's the problem. The math doesn't add up. The volume of water locked in minerals could never account for Earth's vast oceans, over 1.4 billion cubic kilometers. Additionally, the moon-forming impact, a catastrophic collision with a body called Theia, would likely have reset the entire planet's surface, vaporizing any early oceans and sending minerals flying into space. That impact, confirmed by isotope matches between Earth and Moon rocks, adds a critical constraint. Any theory must explain how water arrived or returned after this event. That leads us to the second major theory: panspermia of water. The idea that water was delivered by external sources, primarily comets and asteroids. During what scientists call the late heavy bombardment, the inner solar system was hammered by icy bodies from the outer regions rich in water and organics. For decades, this seemed like the most plausible source. Comets are essentially dirty snowballs. Their impact could, in theory, deliver huge quantities of water to the Earth's surface. But again, the chemistry tells a different story. The deuterium to hydrogen DH ratio, a kind of molecular fingerprint in most comets, doesn't match Earth's ocean water. Asteroids from the outer asteroid belt, on the other hand, seem like better candidates. Meteorite samples from carbonaceous chondrites, ancient space rocks, have water with a DH ratio closer to Earth's. This suggests that it wasn't comets, but water-rich asteroids that brought the first oceans. Still, that leaves unanswered questions. How did these asteroids survive the moon-forming impact? And why did only Earth, not Venus or Mars, accumulate enough water for oceans and life? Every answer opens more questions, and scientists are beginning to suspect there's more to this story than impacts and steam. Perhaps water didn't arrive at all. Perhaps it was part of the very building blocks of planets, present from the beginning in the dust of stars. In recent years, a radical theory has begun to challenge the long-standing narratives that Earth's water originated not from late arrivals or internal processes, but from the primordial ingredients of the solar system itself, what scientists call the solar nebula hypothesis. This theory posits that the cloud of gas and dust that collapsed to form the Sun and its planets already contained water, not in liquid form, but as ice-coated dust grains. These microscopic particles, abundant in the cold outer reaches of the solar system, were drawn inward during the chaotic process of planet formation. If enough of these icy grains became embedded in the material that formed Earth, it could explain the presence of water before any volcano erupted or asteroid struck. More intriguingly, this theory would also explain why water's unique isotopic signature appears not just on Earth, but in trace amounts on the Moon, and even within Martian minerals. The implication is staggering. Water may be a cosmic default, not a miracle, but a fundamental byproduct of solar system formation. But if this is true, why is Earth the only planet teeming with oceans? Why didn't Venus, which orbits just slightly closer to the Sun, retain its water? And what about Mars, whose dry riverbeds suggest a watery past? The answer may lie in a razor-thin window of stability. Earth is positioned in what astronomers call the habitable zone, the precise orbital range where temperatures allow water to remain liquid. Venus, too close to the Sun, became a pressure-cooked greenhouse. Mars, too far and too small, lost its atmosphere and froze. Earth, by contrast, balanced perfectly, but only after a sequence of violent and highly improbable events. The most significant of these is the Theia collision, the impact that likely formed the Moon. While this event would have annihilated any pre-existing oceans, it may have also reset Earth's surface chemistry, allowing for new water delivery and planetary rebalancing. Some researchers now believe Theia itself may have been a carrier of water, a planetesimal possibly formed in a different region of the solar system, rich in ices and volatiles. If so, that means Earth's water may have literally come from another world. Even more provocative simulations suggest that if Theia had struck just a few degrees differently, Earth might have shattered completely, or never formed the moon. No tides, no stable axial tilt, no complex life. So let's be clear, the fact that we have oceans, stable seasons, and a protective atmosphere may be the result of a cosmic near miss. A planetary accident so rare it borders on impossibility. But this isn't just a story about Earth. It's a question that reverberates across the galaxy. If water can be born from dust, if oceans can arise from the chaos of collisions, then life, or something like it, may be far more common than we think. But if it takes a chain of catastrophes that must each go exactly right, then perhaps we are alone, not just in this system, but in the observable universe. And therein lies the existential tension. Is water a universal pattern or an earthly fluke? As new exoplanets are discovered, and missions like the James Webb Space Telescope begin probing the atmospheres of distant worlds, we inch closer to an answer. For now, Earth remains the only place we know with liquid water on its surface. But even here, the origin of that water is still debated, a riddle suspended between lava, ice, and stars. Despite decades of research, high-tech simulations, lunar sample analysis, and asteroid studies, scientists have yet to converge on a single irrefutable explanation for how Earth's water arrived. What we do know is this: every theory from deep mantle release to asteroid delivery to solar nebula, inheritance contains fragments of truth, and none fully exclude the others. It's becoming increasingly likely that Earth's water didn't come from just one source, but from several layered across time. Perhaps initial traces were baked into the planet during its formation, then augmented by asteroid bombardment, and finally sealed by a miraculous collision with a water-rich body like Theia. This composite origin story fits the messy, unpredictable nature of planetary evolution. But it also introduces a deeper philosophical dilemma. If life depends on such a rare cocktail of timing, chemistry, and cataclysm, how often could that truly happen elsewhere? Our instruments have detected thousands of exoplanets, many in the so-called Goldilocks zones of their stars. Yet not one has shown definitive signs of surface water. And that makes Earth's oceans not just a feature, but a fingerprint of an almost unrepeatable process. Still, optimism remains. Mars shows geological scars of ancient rivers and lakes. Some moons of Jupiter and Saturn, like Europa and Enceladus, harbor subsurface oceans beneath ice shells, and new data from interstellar objects like 3I Atlas and Oumuamua challenge everything we thought we knew about cosmic material exchange. What if water isn't limited to planetary systems at all, but travels between stars, hitchhiking on rogue bodies flung across the void? If even fragments of water-bearing material can survive deep space and seed new worlds, then the universe itself may be a delivery system for life. But until we find another planet like Earth, with stable liquid oceans, breathable atmosphere, and signs of complex biology, we remain a solitary experiment, an oasis born from coincidence luck, or something we don't yet understand. And that leaves us with the ultimate question: is water a byproduct of physics or a fingerprint of purpose? Did the universe conspire to create the conditions for life, or did we simply win a cosmic lottery? If we're just beginning to understand the origin of water on our own planet, how long will it take to grasp what's out there and who might be waiting? What do you think? Are we close to solving the mystery, or is this one of those questions that will outlive our generation? And could the next discovery, a single droplet on a distant world, finally change everything we thought we knew about how rare or how common life might be? Let us know your theory in the comments.